Start and see. Host speaking. సార్ వస్తే చేసుకుందాం.
Welcome back to the ECO final community workshop. So today morning we are learning about the blueprint, stage, quantum circuit, and etc. So now I request Dr. Jnan Yalla sir to continue with the further.
Cool. Hello. Hello. Is my voice audible till the end? Okay. Okay. Now, first let's start with the thing which everyone is getting confused from the morning session, and then we can slowly move towards the further topics. Now, okay. So in the morning session, we have seen this zero one thingy, right? Wait a minute. Okay.
One minute, sir. అది లైవ్ ఓకే హోస్ట్ చేంజ్ చేయలేదు.
Okay, good. Yeah.
థ్యాంక్ యూ సార్.
Okay. Cool. So in the morning session, we have seen this zero one thingy through which we got some of the, confusion there. So let me just put it in a very clear manner, which we can follow directly. That is, typically when performing these quantum-based actions or quantum-based operations, we have two types of conventions which are coming into play. One is the convention which through which we're going from left to right, and one another convention is the one which we follow from right to left. So often people will get confused in these type of conventions. Now, so the right to left convention which I've been following is the convention which we'll be seeing in the Qiskit programming language. That's when we're actually doing a programming language in Qiskit. So that's the type of convention which we'll be observing and seeing. But normally when you're dealing with a casual physics kind of thing or casual mathematics kind of thingy, we can directly do it in a casual manner itself. So that's why I will just say that thing, we can follow that thing in a theory form. Okay. And when we are doing dealing with a code actually, at the time we can perform some of the changes, or at the time I will explain you the stuff. But typically in order to do the mathematics, we can just see how it is exactly working right in a simple manner. First thing we can start with this zero one thingy. So in the morning session, I told zero one is represented in this way, right? Instead of this, you guys try to represent zero one in this format. So this is the first thing. Start by representing zero one in an opposite form. Okay, just follow this convention. And when Qiskit comes into play, at that time I will tell you what we need to do. But for mathematics of a theory concept, just follow this particular convention. Okay, so when you take one like tensor of zero, you will be getting an output in this. Sorry. Yeah. And this guy gives me the output like 0, 1 and 0, 0. Okay. So this will be the output of 0 and 1. Okay. So we follow this format. Just follow this format. Because as we are not directly going to Qiskit yet, we can follow this format. Not a problem. Okay. Now, this is the deal. So like this, we can find all the guys. So when you talk about 0 and 1, follow this thing instead of the thing which I told morning. You can follow simply this particular format. Okay, just stick to this particular format. That's why I'm telling this thing again. We can simply stick to this particular convention rather than different conventions to be in the same line. Now, for C naught, for applying C naught, I mentioned this is the control and this is the target, right? This will also be in a Qiskit format. So in reality, or while doing the actual mathematics, you can consider the first guy as control and the second guy as target when we are actually dealing with this type of convention. Okay, we can follow this convention. That's why I'm repeating again. So in this convention, the first guy will be the control and the second guy will be the target. Okay. Now let's try to do C naught of 0 and 1 in this particular convention. In this convention, the C naught of 0 and 1 will look like this. That is, in this convention, the C naught with 0 and 1 will look like, you can take C naught of 0, 1, which says that control is what here? Control is 0 and target is 1. So the output should be what? The output should be same thing. Yes, the output should be the same thing or no change. Yes. Why? Because as the control is 0, there won't be any change with respect to my target. So the output will be the same thing, 0 and 1. Let's try to verify this in a matrix format. So this is a C naught. Okay, that's what we see. Now, the 0 and 1. What is the state of 0 or what is the vector form of 0 and 1 which we took right now? It will be in the form of 0, 1, 0, 0. Try to solve it. What we'll be getting? We'll be getting 0, 1 and 0, 0. Got it? In that way, we will be getting the same output set, that is my 0 and 1. Got it? So we can simply stick into this particular format. Just simply stick into this particular format. Don't think about the reverse, the forward, and okay, just simply stick into this particular format. The only thing what you need to keep in mind is that, like, starting on a reverse number, simply to put in this particular format. That is, for 0, 1 itself, you are doing the reverse operation like this. So, so this one thing will cover all these particular changes or all these particular reverse. So in the morning session, as we took 0 and 1 for this thing, so you need to reverse everything. That is, here also you need to reverse C and T, and then the output will be the same. Got it? So, but instead, if you are just directly reversing here itself, then all these things will make sense. Got it? So just stick onto this particular convention only. Okay? So when we are actually playing with Qiskit, at that time we can discuss about further stuff. But for now, for doing the mathematics or to understand the mathematics, simply get stuck into this particular convention itself. Not a problem. Okay? So yes, this is about the matrix representation. This is how exactly my quantum operations work. Now, now let's go to the superposition states multi-qubit representation. Okay, C naught with respect to 0, 1. Okay, completely already. We found how it works exactly. This is a single state of a qubit. So here we are having two single state qubits. Simply to put, here we are having two single state qubits. Yes or no? Why? Because This first guy is a state of my control qubit, and this is a state of my target qubit. Okay. So simply to put, you are having two single state qubits there. Okay. We are not having the combination of multiple states. We are having simply two single state qubits. But here there is no superposition qubits. Here I cannot see the superposition qubits. But instead, what I'm able to say, I'm able to see two of the like two of the single qubit states, Gani. Not able to see the combination of states. Neither am I not able to see the superposition of the states. I'm able to just identify the single states of more than one qubit. So, and we got to know how that exactly works. Right now, how exactly this C naught and everything will be applied on a superposition state. That's our next goal. Simply to put, first thing, what did I talk about the superposition state? I told like if you apply a Hadamard gate to a zeroth state, it will become my plus state. That's what I observed. That's what I told in the morning. Right? So we'll be using the same concept again. Okay, we'll be using the same concept, which might go like this. But in order to do the same thing, let me just elaborate this thing as well. For that, we need to know about a Hadamard matrix. Hadamard gate matrix will look something like this: 1 by root of 1, 1, 1 minus. This is the matrix of the Hadamard gate. Same like how C naught, X gate, Y gate has a matrix. Similarly, Hadamard gate also a matrix. And this is the matrix which we can see in the Hadamard. Okay. Now, what exactly is plus state? What did I mention about plus state? What exactly is plus state which we've seen in the morning session? 1 by root 2 of 0 plus 1. So this is for a single qubit state. So this thing is happening for a single qubit. Why? Because this zeroth qubit is being converted into a superposition state, but that is also a single qubit only. So a single qubit is going into superposition state. I'm not having multiple qubits here. Now, how exactly I can work with multiple qubits in this point of time? Very simple. Before going that, how exactly you can identify the number of qubits? We are doing only 2 cross 2 matrix operation here, yes or no? So when you're doing 2 cross 2 matrix operation, you are using only one qubit, and yeah, simply do. When you are performing 4 cross 4 matrix operation, there you are using 2 qubits. When you perform 8 cross 8, you are using, sorry, yes. So when you're using 8 cross 8, you are simply using 3 qubits. Okay. So all depends in this way. That is, if this matrix size is 2 power n, you're using n qubits there. Got it? That's the only one thing which you need to remember. So you should not always see the final output of something. Instead of that, you should see how the or I can say you should see the matrix size in order to determine the number of qubits. Another way as that is, if you're talking about the superposition state, you're getting an output in this format, right? In a single ket, how many values are there? So here you can see only one value being there in my one ket. This is a ket, right? So inside that particular ket, how many values are there? I am able to see only one value, meaning I am using only one qubit. Got it? This is one another way to find the number of qubits you are using in the application. So that's why when you're using C naught operation, what is happening? First thing is the matrix is 4 cross 4, giving rise to saying that you're using 2 qubits. And one another thing is the input. Here in a single ket, how many values are there? Two values are there. Thereby telling us that you're using 2 qubits. Understood? That's the primary deal here. Okay? Where this is Q naught and this is Q1 based on the convention which we are following at this point of time. So we just follow this particular convention, not a problem. Okay, now the main question comes like this. Okay, before going to the main question, we can simply solve this as well so that we can see how exactly it looks like and so. So that is, try applying a Hadamard gate on get 0. Hadamard gate is what? 1 by root 2, 1, 1, 1, minus 1. Get 0 is what? 1 and 0. Try to do this operation. What is the output which we will be getting? So simply to put, so we will be getting what? Instead of that, you can just directly try to do it by using 1 by root 2 thingy. So 1 by root 2, 1 by root 2, 1 by root 2, and minus 1 by root 2, and 1, then 0. So you'll be, if you do all the operations, you'll be getting 1 by root 2 of 1 and 1. So thereby giving rise to 1 by root 2 of 0 plus 1. Simply to put. Okay, simply to. So this is how I'll get this particular out. Other if you use here minus h of 1, you will be getting 1 by root 2 of 1 and minus. Okay. So thereby giving rise to 1 by root 2 of 0 minus 1. Got it? That's a simple deal which we'll be following in this point of for this particular thing. Okay? Now, this all are very good when you're actually dealing with a single qubit system. This Hadamard gate works fine when I'm actually dealing with a single qubit system. Meaning, if my circuit looks like this, if this is the only circuit what I'm having, then it completely works fine. Why? Because I simply keep a Hadamard gate here. It works completely fine. Not a problem. But if I'm having multi-qubit system, meaning as explained in the morning session, if you're having a multi-qubit system, which might go like this, that is if you're having Q0 and Q1. So this is my Q0 and this is my Q1. If I'm having multi-qubit system, now if I want to apply Hadamard gate on the first qubit, then how can I do that? So we might think that it's the same operation only, right? Same H operation only. So meaning it's the same H into 0. So that's what we will think. But no, it doesn't work like that, honestly to put. But how exactly it works, Ante, this thing which you're giving is there, na, that should always be the, or that should capture the complete system, not only that single qubit. Meaning, here the complete system has how many qubits? Here my complete system has two qubits, Q0 and Q1. So at that time, I cannot perform this operation. Why? Because this guy only has a single qubit. As this guy has only a single qubit, I cannot capture this complete circuit at that time. So in those cases, what I need to do? I need to apply two qubits, meaning I should apply something like this. While Q0 is 1 is also 0. So that's what I told. Now this is Q0, this is Q1. So I need to apply the complete scenario, or I need to apply the complete qubits of that particular system. Well and good. Now, if I want to perform this operation, let's try to elaborate it. So H had my gate. So there is my Hadamard gate. And how my 0, 0 looks like? Network error వస్తుంది. Hmm? For 11 seconds. Yeah, life actually looks just Okay. Hmm?